let me write it down here. And the topic is magnitude ratio. It's like a transfer function, and transfer function is defined as the output or input in the frequency domain. So you have to convert it into the frequency domain, and that will give it up. So right now this is in the S domain, so S is replaced by j omega. So output of the amplitude output amplitude or input amplitude of the forcing function gives you the this this is a magnitude, and the direction is phi. So phi is the angle, like what is the angle for this one. So this is the basics, and we will solve one. When we solve one problem, you will understand more. So can be you can write down the transfer function, and this transfer function can be written as the magnitude and the angle phi. So angle phi is also in the frequency domain, magnitude is also in the frequency domain. So at the way I look at this, like at usually at a high frequency the magnitude starts decreasing. So let me show what I mean by that. So at higher frequency you will see the transfer function gives a small magnitude. um so for example, if you have a mass here and spring here, and you have another spring here, rather than fixing this end, let's keep this end. um, just hold this like you are holding by hand, and you are giving input. So when you move it, move your hand slowly, move your hand slowly, then the mass will also displace slowly, and the displacement is very high at a lower frequency. But as soon as you increase the displacement of your the magnitude or increase the frequency of your hand input frequency, the magnitude of this mass decreases. But at low frequency, so the magnitude is very high. So you will see that in our question, that it will be more clear to you. So now we have to take one example of the mass spring damper system. I have shown it many times, so I'm going to skip this the free body diagram, but you have to assume that this is a mass spring damper system, and we will replace this the displacement by this. So this can be written as this. Our displacement can be written in the form of big X e to the st in the S domain. So this is our ratio in the Laplace domain. We also call it as a Laplace domain. And then relationship between the two transfer functions. Now from Laplace domain, we have to go to the frequency domain by replacing S by I omega or j omega. It doesn't matter either way. This is imaginary function. So then you have to take the magnitude. How do you take the magnitude of this function? So let me show you over here. This is like a real component. This is an imaginary component. And if you take the I would say this is the mode, the absolute, the real component, real part of this. I'm sorry, this is 2 omega square. So this is the magnitude. And then you will ask me, Professor, what is the angle of this vector? Because this is like a vector, okay? Like I mentioned over here, it's like a vector in the in the real and imaginary plane, and this vector has a magnitude, and the angle is the angle of the transfer function. You see, and what is the angle of a transfer function? This is my transfer function. So you see, if I find the angle, so how will you find out the angle of this transfer function? So the way I will solve this, let me show you 1 second. So what I'm going to show you here, the angle of this one. What is the angle of one in the numerator? You will see the angle is 0 because it's a real part, and minus the angle of the denominator. Okay, minus the angle of the whatever the denominator is, you will write it down here, plus. And then you will tell me that the angle for the real part is like a real axis. Okay, real axis is like over here, and the angle from the origin to this real vector is 0. This angle is 0, but here this is the real part, this is the imaginary part, so we have to apply the tangent inverse rule, that imaginary part will be in the numerator, the real part will be in the denominator. Or if you take the negative sign inside, factor it out or distribute inside, so you can write down like this: tangent inverse m omega square minus k. So let me copy and paste this theory behind the transfer function. So over here, so this is the you have understood about the how to find the angle of the transfer function as well as the magnitude of the transfer function. And I mentioned that the magnitude ratio is the output amplitude over the input amplitude. As I mentioned, this is my input amplitude. My hand is giving a sinusoidal signal, and the signal which is coming out of this mass like a displacement, like b sine omega t. I will say with some lag, because it is not exactly following this same the same phase. It has some lag, because here when you give input at certain time like t equal to 0, it will start following the input maybe at t equals to 0.1 second. That can be represented in the form of a phase difference between the two, um, output response and the input response. So there is some theory behind this. Now I want to show you that the same transfer function can be manipulated to get some more values, useful values. So let me show you what I mean by that. So consider this equation. So if you consider this equation like this one, this is a mass spring damper system. Okay, this is the output response of a mass of the steady state response. So this is our previous lecture. I explained about it. So now what I'm gonna show you that this can be, if you take k outside, if you take this k outside the parentheses, how will it look like? F naught over k. So I can write it down like over here, 1 minus m omega square over k square. I'm sorry, this is not k square, this is k. So the k square is taken out, um, um, and then what I'm going to show you, this can also be written as c omega over k whole square, and c omega over k, or c over k can be written like 2 zeta over omega n, and omega n can be written like k over n, and zeta is the damping ratio, actual damping over critical damping, actual damping over 2m omega n, or can be also written as 2m square root k over m. So m, so this can also be written like 2 square root k m or mk. Like let's follow the book notation, they write down m first, but it doesn't matter, it's just a commutative, so you can write down any. So with these values, and r, what is r? The forcing frequency divided by the natural frequency. So with these terminologies, I'm going to show you this can be written like a output amplitude can be written in this form. So let me show you this form. So over here I can write down, rather say I'm saving time, rather than me writing down everything, I will just show you how to write it down in or the book. So it's the same thing, they took out k outside the parentheses from this 4.1-15, and then they rearranged everything and wrote down this equation. This is a useful information, as the ratio zeta is, if it is 0, then what do you get? So it is very close to this. So now what the angle, for the angle part, how can you find out the angle? So this is the formula for the, like this is the angle of the, like this is the imaginary part. Okay, this part is imaginary part, so therefore it is in the numerator, and this part is a real part, therefore it is in the denominator. And then when you write down, this is the magnitude, sorry, this is the magnitude of the output response. How about the steady state response, including the, like this, did I explain this? Yeah, the b sine omega t plus v. So b is like x, x omega. So if I write this down, steady state response, so the same magnitude which you wrote down, this one, the same um magnitude, and times the sinusoidal function, which is including the phase difference or the phase delay. This is a steady state amplitude formula, the steady state magnitude. And if I write down the steady state magnitude ratio, as I mentioned, the magnitude ratio can also be written in terms of m equals to x over f. Let me show you. Did I say? Yeah, this is the magnitude, m equals to x in the omega domain, because as the frequency changes, the amplitude of the output response also changes. It goes, as I mentioned, that it goes to a smaller amplitude when the frequency increases, and this is the for most of the, this is the same case for any mass, like. And then f naught, x over f equals to magnitude ratio. So I can write down the same thing in this form of a magnitude ratio, equation number 2-17. So what I did over here, rearrange, I'm sorry, this is what I did over here, just rearranged the same. f naught goes over here, and when you cross multiply f naught on the other side of the equation, then you are left with 1 over k, this term. This is the magnitude ratio. And then for low frequency, when r, for low frequency, what will happen for r approximately equal to 0? R is what I mentioned earlier, that the forcing frequency divided by the natural frequency. If r is approximately equal to 0, what will happen if this goes to 0, this goes to 0? So you're left with 1 over k. So a steady state amplitude will become like a static displacement divided by f naught 1 over k. Or this, like, steady state become like a static deflection. You see what I mean? So I can write down static deflection of the spring, it equals to f naught over k. You might have heard about this formula, f equals to kx. Sorry, this is kx. So x is a statically displaced. When you attach the mass, it deflects a little bit, deflection happens, and that deflection is due to the mass and the weight. So this goes down, like this is my steady state, sorry, static deflection. So this is almost the same. So I can write down here, rearrange everything, the km. If you multiply this k with this m, so you're left with 1 over 1 minus r square whole square plus 2 zeta r. So I just multiply km, and that is what is km equals to. We know that the km equals to x over. So I can write down as x static actual displacement divided by the static. It's just like what we are doing. Let me show you what we are doing. We are actually using the dimensionless parameters. So dimensionless, we want to make the ratio of the mass divided by the static deflection. What is that formula? So let me show you over here. So these equations, okay, let this equations, they will you can use them in your questions, homework problems, which I'm gonna assign you soon. So here, as it is mentioned, I was talking about when there is at low frequency, this becomes 0, this part becomes 0, and you're left with f naught over k. And steady state displacement can be written as the static deflection. And for dimensionless parameters, x in the numerator, actual displacement divided by the static displacement, it is mk, which is equal to this answer. And steady state displacement when r equals to 1, when you plug in r equals to 1, this goes to 0, and you are left with 1 over 2 zeta r equals to 1. So you're left with, so static deflation at frequency equal to the resonance, the magnitude of the mass be over the static deflection equals to 1 over 2 zeta. Another formula is useful, a that at high, and like what is the frequency or the peak frequency or the damped natural frequency. So the peak frequency is little bit less than the resonance, a little bit small, because you are subtracting. If zeta is, suppose zeta is 0.1, so you are having omega p is a little bit smaller than omega n. Let me show you a graph so that you will understand more clearly. So what I'm explaining here, so in this graph you will see, So this r equals to, this is a little bit crooked. So this is the zeta equals to 0. As zeta goes smaller and smaller, the amplitude of the mass increases rapidly, and zeta approximately is 0, then the amplitude goes to infinity. And what happens to the phase difference? So phase difference, you will see whenever there is a change in angle, 90-degree phase, um, from here to change to 180. Whenever there is a change, it means the resonance is happening at the at the change in angle. What it means, let me show you. Let me show you physical meaning of this mass. Suppose if this mass is, um, let me show you. Suppose this mass moves, is moving up, that it is following, it is following the phase at low frequency, but at high frequency the phase difference is become, it becomes negative. That's what it means physically. So you apply force downward, but at high frequency the mass moves upward. So they are opposite, by a 180-degree phase difference. So at a frequency, apply frequency, you see the 180, you suddenly it flips. So this is what it means. So whenever you see in the phase diagram, the whenever you see the angle is changing from 0 to 180, it means there is a resonance occurring at that location. So that's what it means from the graph. So the amplitude ratio E omega p's can be found by this formula. This is also in the table, and the amplitude of the, peak, um, amplitude can be written. So when you are doing homework, look at table 4.1-2. It is very useful table for you. So we have covered all this. Let's do one problem. I want to show you one problem here. So let us solve this problem together and use the transfer function. Use the transfer function given below to find the steady state response. So the transfer function, the output over input, that is also known as the transfer function estimate. So replace S by frequency. So S by I iota omega. So I can write down the, let me write down the magnitude. So they are asking you, so use the transfer function, find the steady state response. So let me show you. The steady state response in the time domain can be written as the magnitude and sine omega t plus phi. So we have to find out phi from this transfer function. We have to find out x from this transfer function. So let's do it. I just mentioned that the x can x omega. Let's go to the table. I want to show you from the table. Where's my table? Here, this is my table. So I want to grab this formula. X. I believe I showed you here. This one is the it's the same thing. Hmm. Let's use this equation. Okay, look. Applied force is 20 sine omega t, where F naught is 20. Omega is 0.01. Okay, and the remaining, this is our question. So it's the same thing. F naught over. I'm gonna plug it in everything here. So X, because my main objective is first of all, let's find out the magnitude of the output response, the steady state response, the magnitude, and then plug it. So in place of F naught, can I write down 20? Because this is my 20 given in our question. So I can write down 20 here. So this is in the form of a like a omega square. Um, I'm sorry, there is you have to replace S by I omega. So what I can do here, I have to do a little bit rearrangement here. So I can change this transfer function. Let's change this transfer function in the frequency domain. I can rewrite here. And then let's do this 1 minus 40 omega square plus 14 omega iota. I'm sorry. So this is my transfer function. So how will you find out the magnitude? The magnitude can be found. This will remain the same. The real part square, imaginary part square. So let's do this. 1 minus 40 omega square whole square plus 14 omega. This is omega, okay? Whole square. So let's do this. So what I'm gonna show you, you will ask me, Professor, what should we plug omega in this? So I'll tell you that it is given in our forcing function, because frequency does not change in the output response, only the phase is added, the frequency remains the same. So what I can do here, I can replace this omega as 0.01. So let's do this together. So open your calculator and help your professor to see what do you guys get. 1 minus 40, 14 times 0.01. Okay, this is my magnitude of the transfer function. So if you do this, you get 4.971. You can compare if you do the math and let me know in the chat box. I can watch the chat box here. So what do you guys write down in the chat box? Do you verify this answer is correct?
Professor, I have a question.
Yes.
For this problem, can't you just take the MC and K um, function and just use that in the first equation you had?
This one?
Because it's in the characteristic. Yeah, like the MC and K constants are in the characteristic equation of the transfer function, right? So can't you just use those constants in that x omega equation? Like
Yes,
for like
like you are saying, I think we are using the same thing, right?
yeah, this just seems more work, kind of, but yeah.
Do you get the same answer 4.97 none?
Yeah, I just did it a different way.
But does it match?
Yes, I think it. Yeah,
Okay, that's good. If it matches, then you can use that way. I will give you full credit one when I will see the results in my quiz. I'm gonna I'll announce the quiz later, but let's focus on the phase. Now, after you do the magnitude, you have to find out the phase of this transfer function. Phase is negative tangent inverse. Negative because it's in the denominator. So I'm gonna write down the real part, imaginary part first. 14 omega over 1 minus 40 omega. So let me write down here. I'm gonna write down a little bit. Let's make it shorter so I can write down here the real imaginary part here in the numerator. So if you do the math here, so let's do this together. So minus tangent inverse 14 times 0.01, which is 0.14, and this is because 0.996. And in radians, what do you guys get? Negative 1.1396 radians.
That's what I got.
You see, you're getting the same result. So now let's focus on our output response. This is my steady state. So I'm gonna grab this formula and plug in the values of my magnitude and the phase. That way I will finish explaining the output response at a certain picture. When I say certain picture, means of omega is at 0.01 frequency, which is very very small, like it's a DC value, it's almost zero, like it's not having higher frequency. You see my point, guys? So let me show you here. So I'm gonna write down the complete steady state displacement. Steady state displacement is 20 times 20 times t omega. So make sure you multiply by the f naught here, which is 20. Okay, so then because I did not multiply by 20 in the beginning, I just wrote down like this, and you have to multiply by 20. So 20 times point, how much? Sorry, 4.97. Let me write down 4 point. Point zero one t minus. So this is a complete steady state amplitude at any time at a frequency of 0.01 t. So you can solve some of the problems at home. When you go home, solve these problems. I'm gonna assign you today for the chapter 4 homework. So let's do another problem. So let me show you another problem here. So the question is the equation of a certain mass spring damper system is given. So let me move it a little bit here. The equation of motion of a mass spring damper system is given like a 5x double dot cx dot plus 10x, where f of t is in the form of a sinusoidal input, and determine the magnitude ratio m equals to x over f. Determine the natural frequency. Determine the peak frequency. Determine the peak magnitude ratio. For zeta, let's do with 1 zeta equals a point 0.1. So let's do this together. So you now let's do this. What is omega n? Square root k over m. This is my k value. This is my c value. This is my m value. Square root k is square root k over m. 5 times 2t. This is my resonance or omega n, where k equals to 10 from the equation of motion. Natural frequency and the peak frequency. The formula for the peak frequency is this one. I believe it is 2. Let me double check. It is 2. Yes, it is 2. And one more, the peak ratio. So this is my peak ratio x over p. So let's plug it in. Omega n is equal to square root 2 square root 1 minus 2 0.1. Let's use this one. So can you help your professor doing the calculation? Do you get 1.4?
Yep, I got 1.4.
That's good. Christian says is God says. So that's good. We have found this answer. So anybody, let's do the next point. So I want to show you that we have found 1.4 radians per second. This is my 1.4 radians per second. The magnitude ratio, the formula is 1 over k. At the peak, the magnitude at the peak, it is this form: 1 minus 2 z, 1 minus zeta square. So if you plug in 1 over k as 10, so it is 10. This is my 10. Okay. So let's try this one together. I want to just write it down here. Square root 1 minus 0.1 square times 2. This is my, so I got 0.5. So this is my magnitude ratio. Do you verify, guys?
Yep, that's what I got as well.
So that's what we have to do this way. So now you can solve problem number 1 through 10, or maybe problem number 1 to 3. So let's move forward. I just solved a few problems, but remaining problems you can solve. I'm sure it's not difficult. When you go home you can try, and I have made some videos, more videos for you to look into this to understand the resonance and the transfer function. Now, how can I write down the magnitude in the form of a dB? So, like we can write down the decibel, the magnitude ratio. Instead of plotting the magnitude ratio, we can use this dB value. M equals to 10 log of m square. So this 2 comes in the coefficient, multiplied by 20. It's a logarithm function. Everybody knows at this moment. So this is the definition of a decibel, that you take the value of 20 log base 10 of this, and if you want to convert it into exponent form, so m equals to what? 10 to the m over 20. This is just you can convert a logarithm into exponent form. So now when, for example, m equals to 10, if m equals to 10, so if m equals to 10, what will happen? Log 10 and log 10 base 10 equals to 1, so m equals to 20. 20 dB. We call it 20 dB. And if m equals to magnitude if equals to 1, it is the dB value is 0, because log of 1 is 0. So m equals to 0 dB. And value of m less than 1 will have a negative decibel values. So if the magnitude ratio is suppose negative, I'm sorry, less than, not negative but less than 1, less than 1, what will happen? Suppose m equals to 0.1. So what's that? So I'm gonna write down log of 0.1 is negative 2.3 and multiply by 20. So if you multiply by 20, so you get what? Negative 20 dB. So what is that? Is it like once m is equal to negative? Okay, that the thing is, I want to show you that why am I doing this explanation? That when you are doing, let me write it down here something. When the magnitude, when the value of the dB is -3, then below -3 you're gonna remove it from there. So what I mean by that, for example here, let's, so you will see that if at a certain frequency, for example, if mp, oh sorry, let's take it. If m is equal to maximum magnitude ratio divided by 2, then suppose if your bandwidth like this, and this is the maximum amplitude, which is mp, and these are the frequency, this is my frequency axis, okay, my frequency axis, and this is my lower limit, this is my upper limit, and I want to find out the limit that which magnitude I will consider for my reasonable amplitude. So I will keep this amplitude above mp over square root. If I'm above that values, then I'm having meaningful amplitude ratio. But as soon as I go below this, so it's not prominent, it's not dominant amplitude. So that's how we do the filtering, or the what we call the bandwidth. Suppose if you have this, I'm sorry, this is why suppose this is my maximum amplitude and this is my limit. So it looks like a low pass filter, and this is known as a cutoff frequency. What is this frequency? It's known as the upper limit, which is also cutoff frequency. You don't worry about the magnitude below the value. So probably I'm trying to explain you, but when you go home, you try to read this section of the resonance and the bandwidth. But before, let me show you the same magnitude ratio. This is the mass spring damper system, and equation number, new equation. So I can we define the dimensionless value. So I'm going to replace this in the form of a dB, 20 log dB. So you have to take the dimensionless value. How are you going to take the dimensionless? So if you write this kx over here, kx is what? Force. So if you write this dimensionless value, so I can write down the same thing like this. So now this what is this amplitude? So, or I can write out m equals kx over f naught. The output amplitude divided by the input amplitude is the magnitude ratio. So I can write down this ratio in this form, and then I will write down 20 log of this magnitude ratio. Whatever I wrote down, this one is gonna come over here, and then I plot it in the form of a frequency. In my x-axis, it is the frequency x. Sorry, this is x-axis, so this is my frequency ratio r, and the y-axis is my m, decibel of the magnitude. So at 0 means like at magnitude, when magnitude equals to 1. What does it mean? Means I mentioned earlier that the mass, if you are holding the mass and you move your hand slowly, maybe I probably yeah, if you move your hand one string, you have attached the mass with one string, the below elastic like rubber band, and if you move your hand slowly at low frequency, the same amplitude which you are inputting, you are getting the same amplitude. So magnitude ratio at low frequency, like very small, is I would not say it's less than 1. So you will have the same magnitude. Whatever you are inputting the displacement, the mass will go down with 1 centimeter down, 1 centimeter up, 1 centimeter down. But as you go above the resonance frequency, then it becomes changed. So let me show you the plot. You can understand more from the plot. I'm going to show you the logarithm plot. So that way you will understand more clearly. So over here, so when plotting m value of the dB in the frequency domain, it is customary to use logarithmic scale for the frequency axis where m and phase. So I'll show you both the magnitude in the dB as well as the phase angle. So and note that m goes to 0. You see, at high frequency, m goes to 0. What will happen? It will touch this line. It will touch somewhere here at a very high frequency, like r. Suppose r equals to 1 here, and r equals to 1 means a very high amplitude. You see my point, guys? So it will look like this, and this is the peak. You see my point? So the decibel very high over here. So but as you go further, then higher frequency, as you keep on increasing the frequency, forcing frequency is higher, the amplitude of the output displacement goes down. That's what you're saying. So let me show you the plot. Now you are understanding the plot in dB. We call this as a 1 decade. And what happens to, so like it's 1, so this is 10, this is 100, this is 1000. Or it is for the split, I'm sorry, this is for this divided into 10 digits. 1 2 3 4 5 6 7 8 9 10. Maybe it is for the divide, but anyways, this is not uh, it's not a big deal, but you can see that the at resonance frequency you have a maximum amplitude, but as zeta value increases, the amplitude, the peak decreases. And I want to show you the phase difference, and you will assume you can estimate the phase angle, the phase difference. Let me show you. I believe that the phase changes from 0 to 180 at resonance. So this is my 180 change. So like initial displacement is positive, but the output response is negative at resonance. So that's why. So phase angle, you can easily judge that where is the uh, angle changing. Wherever the angle is changing from 0 to 180, it means that is the resonance occurrence at that location. Then comes the next topic about the resonance and the bandwidth. Now here we are having the damper without damper.
It looks like from that above plot, the resonance will be minus 90 phase angle, right? Or am I reading that wrong? From that.
Like from 0 to 180, you see the difference? Phase angle changes.
Yeah, so if a resonance where the forcing frequency would equal the natural frequency, that would be 1, right? So that goes up to 90, minus 90.
Yeah, minus 90 is that phase angle. You are
Oh, you
right.
said 80. All right, all right.
So now the bandwidth, as I mentioned earlier, over here, let me show you the this plot here. So this is the cutoff frequency. Cutoff frequency is the frequency where the less than the amplitude of the cutoff frequency we are not taking it into consideration. So you have to understand that there is a low pass filter. What is the bandwidth of the low pass filter? What is the bandwidth? So in this case, look, this is the band pass frequency means the like some frequencies can pass in the like maybe from 10 to 100. In this kind of device or transfer function or the filter, when you are restricting your mass to respond only in certain bandwidth, then you will use your functions as you will use. So it will automatically use the band pass. So we have to see where does the mass respond. So then comes the displacement here. So let me show you here. Assuming this is undamped case, so this is a steady state response. And the forcing frequency is omega. And then comes another concept of the beating. If the forcing frequency is close to the natural frequency and the force response is this, we can rearrange everything and it looks like this is sorry this So it means that this is the when the forcing frequency closes. So this one is the amplitude of cosine wave. Cosine wave is um this is a sine wave. The cosine wave starts from here, like maybe from here to here, and this is sine wave here to here. This is magnitude. So let me write down another equation here. So final answer for the steady state displacement can be written in the form of a sine wave. And the amplitude is 2f naught over m omega n square minus omega n omega square. That amplitude varies with the frequency difference. So you see, this is the difference. So the beat period, time period 2 pi over omega n. Well, the vibration period is 2 pi over one less. This is the beat period and the vibration period and the resonance. So it will look like this is that example of beating when the forcing frequency is very close to the natural frequency. So it will have some components higher frequency, so vibration is happening. So if you consider this is like a sine wave, and then it has some higher frequency components here inside. So the natural frequency, when the forcing frequency is equal to the natural frequency, it is resonance. So let me show you the final formula here, which you can use in your homework problem. Leave this one, yes. Another problem is the solution. Yes, sorry, therefore magnitude ratio and some of the band pass filter and bandwidth example. I can show you some of the examples of the bandwidth, how like band pass filter, low pass filter, you can identify from the look at the graph. So the first graph is telling me the magnitude. This one is MP over 2 is a band pass filter, but here this is low pass filter. You see slow pass a lot, but this is not, we are not interested. And this is high pass filter. So up until above the MP value, you see my point? I'm just guessing. This high pass filter is this one, and system having two bandwidth regions. So it is useful for us, and when we are doing the acceleration or displacement terminology. So how do you design instruments at when you want to find out the resonance? And here's the example of vibration instrument. This is a mass spring damper system, and the output is the z over y. Z is the difference between the x and y, so I can write down here. In this, I can write it down here like this. So an accelerometer, what happens an accelerometer, you use very small frequency for less than, like, I believe less than 3. Let me show you over here. So when you're designing instrument as an accelerometers, so is the frequency is a low side, and the vibrometer it is above 3. So above 3 it will be used as a vibrometer, and less than 1 it will be like used as an accelerometer. So this is how you will find it out. We will start from here next time. I'm gonna assign you a homework related with the with this lecture. All right, guys. I'll see you next week. Thank you.
Thank you.